Hey guys, Will here. So, before we even discuss anything about black holes and stars, let's think about why we're interested. Well, we are currently being in an elliptical orbit around a black hole. So, well, that's plenty of reasons to care about it. So, let's go ahead and get into why we're caring about it with physics. Ooh, big fancy stuff. So we have the change in momentum over change in time. This could be split up into our magnitude and p hat, so magnitude and direction, if you will. And when we take the dot product of that, we have two separate forces from that net force. We have the parallel force and the perpendicular force that make up that net force. So, as to think about what each of these mean. If I have the parallel force, right, and that's equal to 0, then I'll have a circular motion. This makes sense. It means that the amount of tangential acceleration, that tangential force, if that's equal to 0, that means that nothing will change. Likewise, you have a circle. But let's say that it does change. Let's say that we have this man called Kepler, right? He says that if this does change, right, it's not equal to 0, right? Well, that means that I'll have an elliptical force, elliptical motion. And that means that the force is not constant. It means that as we change our positions along this ellipse from perihelion, meaning the closest to this black hole, to the farthest, we're going to have changing forces. So we're going to go ahead and use an equation to represent this changing force. We're basically trying to say that if I have a big force, then that means that the distance must be small, as given by our gravitational equation over here, where it's inversely proportional to each other. Likewise, if I have a small force, then I will have a big distance between the two. Now, when I rearrange my equation to have things that we could solve for example, some things that we could solve for is the net force from the first equation. Since we're pretty much given everything we need, mass, position, time, so we could solve for the net force. We could also use the givens such as the positions of the star and the mass of the star to calculate what is the mass of the black hole in an elliptical motion. And now we're going to go discuss the coding. Hey guys, and we are back. Think of this part as the initial part of our code. Right now we're going to have the setup where we have the initial conditions, right? We're going to plug that into our givens that we talked about earlier. The only real tricky part about this code, as you guys can probably see over here, is our indexing. Indexing is just where we find x and y components pretty much of our velocity. That's it in a nutshell pretty much. When we know the x and y components, we can find the perpendicular and parallel forces. Thus, since we know the summation of the two is our net force, we could then plug it in as a magnitude over here in our equation. So let's go on how that'll go under a while loop. Alright guys, now let's go ahead and talk about what happens inside of that index loop. So over here I have my initial conditions. The only difference now is that it'll all be in terms of the indexing. So for example, since I have my x and y components in the index, I'll be taking in terms of velocity and momentum, which will then give me, as everyone loves and knows, the net force. Furthermore, it can be divided into the parallel and perpendicular forces for graphing purposes. Now, when I solve with initial conditions, given the net force, and the conditions from before, just given to us from the worksheet, then we could go ahead and find the mass of the black hole. So, let's go ahead and start code and see just how much mass we have. Alright, so let's go ahead and get started with the recording now. So, let's go ahead and run the program for a tab. Now, as it starts to go around the black hole, notice how the arrows, which represent the vectors, get bigger. This is because, as we said earlier with Kepler's second law, if it gets close to that superstar object, right, it's going to have a larger gravitational force. But once it gets farther away, it becomes really small, as shown in the graphic. Now, the mass of the black hole is given on the bottom. It's 2.4 times 10 to the 34th kilograms in this case. And we're back. Alright, let's go ahead and answer some questions now. What does it mean? So we found a force and we found its momentum. What's the difference between the two, specifically its parallel and perpendiculars? Well, I'll give a quick generality. Momentum is something that you could really see. Force is something that you could more of a feel.
See, both of them are very related concepts. Momentum over a certain change in time will give you the force. However, you could only see one of them, the momentum, and you could really only feel the force, if that makes any sense. So the force is more of a consequence of momentum, if you want to think about it like that. Now what if you have a black hole, you replace it with a different black hole, everything else stays the same, the elliptical motion stays the same, the mass of the star stays the same, etc. Could you tell me what the new mass of the black hole is? And the answer is no, we couldn't. If we go back to the equations earlier where we rearranged that gravitational equation to find the mass of the black hole, well, we're going to be stuck because all of our variables were fixed. And since we have no free variables left inside of that equation, we'd have to do another kind of concept that may or may not be outside the scope of this class. Alright guys, that's it for the video. I hope everyone learned something today, and have a beautiful day.